Guys, it's your boy Toomer Teaches. Back at it again with another sick video. Um, Bad intro aside, let's get right to it. I'm going to preface this by saying that periodicity is probably one of the most important topics that you'll be covering. I would say bonding is pretty much number one, but this takes probably a close second or third because it is that important. Now, without ado, let's get right into it. Um, so, firstly, we need to talk about electrostatic forces of attraction. Electrostatic forces are forces that hold charged particles together. They are forces that charged particles exert upon each other. Um, Opposites attract, like charges repel. That should be obvious from grade school. Um, Electrostatic forces are stronger as the distance between them decreases, and the electrostatic forces are stronger between particles of greater magnitude than of lesser magnitude. We can summarize all these ideas using a little known thing in physics known as Coulomb's law, where F equals K Q1 Q2 over R squared. Now you might be wondering, why is distance? You might be wondering, where does distance squared come from? Because we clearly did talk about distance, but why is it a square relationship? Uh, Ask a physicist that question. I'm not going to answer that, but what I will say is that this square here is actually really important, and the main premises I want to take away, I want you to take away from the first 2 minutes of this, is that distance is far more important than the magnitude of these charges here. Distance plays a much stronger role in determining electrostatic forces of attraction because it's squared, and if you square a number, it gets bigger, and then dividing by a bigger number yields you a smaller force because that's how math works. Um, anyway, with that aside, I'll be coming back to this uh, pretty regularly, so just keep that in mind. So, without further ado, Let's go into the actual trends. So there are several trends that you're expected to know and recognize. The first of which, and what is probably the easiest, is atomic radius. The general trend is that it increases going down. In particular, it increases as you go um, to the left and down and to the left. Similarly, it decreases as you go up and to the right. Um, and there's two. We first, let's explain the vertical trend, and then we'll explain the horizontal trend. It's easier just to work that way. The reason for the vertical trend is pretty simple. As you, according to the Aufbau principle, you fill electrons in from lowest energy to highest energy, and as you go down, the electrons have more and more energy because there's more and more of them. Well, yeah, that makes perfect sense. But anyways, you're going, the highest main energy level that you will encounter in that atom is further away from the nucleus, so therefore the atomic radius, the distance between the nucleus to the edge of the atom, is bigger, just because those higher energy levels just sit further away from the nucleus. We can clearly see this here being demonstrated using these electron shell diagrams that you may have seen in middle school or whatever. So as you can see here, lithium, there's a +3 charge there, +11, +19. But as you can clearly see here, this is energy level 2, and then energy level 3, energy level 4, and as you can clearly see here, these are further away. Energy level 4 here is further away from the nucleus here than lithium is here and here. Like, that distance is much smaller than that distance. So that's really all that says. Um, the horizontal trend is also quite simple to explain. Um, Basically, what it amounts to is that since the electrons are in the same main energy level, the higher charge of the nucleus causes a higher um, force of attraction. The higher charge of the nucleus causes a higher force of attraction, and therefore that pulls the electrons in closer because they are like charges and they will attract to each other. Now, you might be wondering, why isn't the electron just crashing into the nucleus? Um, to put a long story short, it's due to something called centripetal force, and the electron is basically moving fast enough where it can orbit the nucleus. However, ask a physicist more about the details. I am not a physicist, I am merely a chemist. Um, so, as you can clearly see here, fluorine, which has a +9 nuclear charge, has a much smaller radius than lithium, which has a +3 nuclear charge. As you can clearly see here, the electrons are getting closer and closer because of that higher nuclear charge. Um, so that's a pretty simple explanation, I think. Um, the next trend that you're required to know about is the first ionization energy. And before we talk about the trends and stuff, let us first define what that is. So the first ionization energy is the minimum energy required to remove the highest energy electron from an isolated gaseous atom. This is the chemical equation to go along with it. This one that I've highlighted here on my screen. So what does that mean to you? Because that sounded like a lot of mumbo jumbo. It's essentially just a measure of how strongly an atom attracts its own electrons. Or more specifically, it's a measure of how strongly an atom attracts its own valence electrons. So the electrons on the outermost energy level, the highest energy level, the outermost electrons, same thing. And the trend is that as you go up and to the right, first ionization energy increases. In fact, no, ionization energy just increases in general. As we noted in topic 2 for the higher levels, there are jumps, and those jumps help to explain the whole energy level concept. However, standard levels don't need to know that. What you need to know is that as you go up and to the right, that ionization energy increases. For the vertical trend, it's quite simple. They occupy lower and lower energy levels, and that means the electrons are closer to the nucleus. And as we noted here earlier in Coulomb's law, which I will pull up again, handy dandy it is, as we can see here, that distance is getting smaller, and dividing by a smaller number yields a larger force. And as we just stated before, distance is more important than charge when determining the net force of when determining electrostatic charge. And then as you go, so that explains the vertical trend, that it increases as you go up. The reason is because the energy levels are closer to the nucleus. That means the electrons are closer, and that means the distance is minimized, and distance squared, squaring a small number yields a small number. I should say smaller number, but technically that's not correct if we measure everything in picometers. Anyway, this number here is minimized, and that means this is maximized, because that's how math works. The horizontal trend, what's important to note is that since all the electrons across a period occupy the same energy level, this distance here is constant, more or less. It might vary a little bit, however, those variations are negligible, and that means since this is constant, so this is held constant here, that means increasing the product here, so increasing, so let's call the nucleus Q1, increasing Q1 directly increases the force of attraction felt by that electron. So that means since there's more force holding the electron in, it is harder to remove. And similarly, since there's more force, and similarly with the vertical trend, since there's more force as you go up, the electrons are harder to remove, because you have to fight that force more or less to remove it. And similarly, as you go across the period, since there's more force holding the electron there, you need more energy to remove it. Note that there are many discontinuities in the trend, which we talked about in topic 12, I think. However, for the sake of mentioning them again, I'll mention them again. There are gaps, periods 3, groups 13, 16, groups 13 and 16 have lower than expected ionization energies. That's because for the case of group 13, removing an electron causes the orbitals to be full. Like every orbital is full of electrons, and that is a somewhat stable configuration. It's actually a stable, there's a degree of stability associated with that, I should say. having full orbitals and sublevels. So therefore, nature tends towards stability. So therefore, the ionization energy is not quite as high there in order to favor that more stable configuration. And then for group 16, it's just a matter of, again, there, except there's a degree of stability associated with half-full orbitals. The reason that is because there's no electron-electron repulsion within the orbital, so Hund's rule is obeyed. Well, obviously everything obeys Hund's rule, but Hund's rule is more obeyed, I should say, because the electrons are unpaired, and that means there's a degree of stability associated with that, so therefore it'll try and reward that higher stability by lowering the ionization energy. Oh, wrong thing, but here's the graph just to sort of back up what I was saying. So we can see here, that's group 13, that's group 16, 13, 16, 13, 16, 13, 16, I think. I don't know. This one's kind of weird. Probably because of the F block. Sorry. So that I just explained. The next trend that you're required to know about is electronegativity. Basically, the formal definition of electronegativity is something you don't need to know, but what you're expected to know is that essentially it's just a measure, it's a tendency of an atom to attract valence electrons of other atoms to itself. So basically, that's what it is, more or less. So to form covalent bonds, atoms share electrons. They do this to achieve noble gas configurations. However, what we're going to talk about in topic 4 is that this sharing is sometimes uneven, and this is the reason why. So electronegativity is a tendency of a atom's ability to attract valence electrons to itself, of other atoms, of course. And electronegativity increases as you go up and toward the right. The vertical trend, it's basically like the ionization energy trend, but for the sake of explaining it again, as you go up, the energy levels get closer and closer to the nucleus, and that means this distance here, the distance is smaller and smaller, which maximizes the force of attraction, which, as we saw with Coulomb's law, distance is more important than magnitude of charge. However, when determining this sort of stuff, so although the things at the bottom have a higher nuclear charge, the smaller distance of the smaller atoms, the smaller atomic radii, minimizes the distance, and since it's an inverse square, the force is maximized. So therefore, the electronegativity goes up as you go up, because the forces of attraction are maximized between, well, what would be the valence electron of another atom and the nuclei of the atom that we're talking about here. Similarly, as we go across to the right, since distance is constant because we are occupying the same, all the atoms are in the same main energy level, that means the distance is constant, more or less. There might be variation, but since that's constant, increasing the nuclear charge increases the electrostatic force felt on by electrons, and that means, there's a higher electric force pulling electrons in, both the electrons within the atom that belong to the atom itself and valence electrons of other atoms. It causes a stronger electrostatic force being felt on it, and therefore it has a higher electronegativity. And you could apply that same logic to the vertical trend. It's actually a very important trend because it comes up a lot in bonding and determining all sorts of stuff. So you might want to remember that one. Electron affinity, it follows the same trend as electronegativity, and it follows the exact same logic. However, this trend is a little bit less consistent. The trend is that as you go up and to the right, electronegativity gets more and more negative. It's more exothermic. However, this trend is rife with exception. As we can clearly see here, chlorine is a more negative one than fluorine, and then the trend is somewhat consistent. But then as you can see here, negative 27, negative 122, greater than 0, minus 141, and so on and so forth. So this trend is clearly not as consistent as some of the others. Uh, so I'm not going to explain the trend again, but it follows the same logic as the electronegativity one. So just replay the video from that section where I explained it quite in depth, because it follows the exact same logic. Some notable exceptions: oxygen and fluorine have less negative electronegative EA values because they're small atomic radii. Basically, since the electrons are so close together, putting in an electron causes a lot of repulsion, internal repulsion, since they're so close together, and that means it doesn't want to insert. Groups 2, 12, and 18 all have full energy of sublevels and therefore are relatively stable and are resistant to adding electron. Group 15 ones have relatively less values, because those half-filled sublevels we talked about earlier. And yeah, the next sort of section of this video, which is getting quite long, we're going to be talking about metallic and non-metallic behavior. Sort of what behaviors do they play? When ions are found in compounds, when elements are found in compounds, they could either be ionic or covalent. And in the case of, anyway, let's cut to the chase. Since metals have low ionization energies and low electronegativities, they tend to lose electrons and form cations. Non-metals have high electronegativities and high ionization energies. This means generally they tend to gain electrons and they form anions. And specific ion charges relates to the particular electron configuration of the element, how many valence electrons it has, and how many electrons it must gain or lose to achieve a noble gas electron configuration, which is pretty much always the name of the game, to achieve one of these. And for main group elements, predicting charge is quite easy. For transition metals, it's quite difficult. The only things that SLs are expected to know is these common examples here, and that generally transition metals usually have a +2 charge. So deriving these charges is quite simple. +2 and +1, they're metals, they'll tend to lose electrons, and as we talked about in topic 2, the group number for the first 2 is equal to the number of valence electrons they have, so they lose 1 valence electron for group 1 and they lose 2 valence electrons for group 2, well, both of them. And then they have noble gas electron configuration, so they have +1 and +2. For groups 13, they tend to have 3 valence electrons, so just subtract 10, and then 3 plus, and then 4 plus 2 plus, and then at group 15, since there's more electrons in orbitals than there is that needed to be filled, they now just tend to acquire minus charges. They also have high electronegativities to help with that, so it's 3 minus, 2 minus, and 1 minus, because there's 3 holes, 2 holes, and 1 hole respectively they need to fill to get their noble gas electron configuration, which is more than which takes more work than removing 5 electrons or 6 electrons or 7 electrons. And the same periodic trends that we discussed here can also be applied to ionic radius. Basically, provided everything is in the same group or period, you can use those same periodic trends with ions as well. So what's important to note, though, is that anions tend to have larger radii than neutral atoms, which have larger radii than cations, because having more electrons causes a bunch of repulsion. So having more electrons in than is normal causes a bunch of repulsion, and that means that repulsion will spread out the electrons more and cause the radius to increase. Similarly, if there's less electrons there and the proton charge stays the same, there's more electric force felt by each individual electron since there's less electrons causing internal repulsion. Isoelectronic ions are ions with the same electron configuration, and going across a period, ionic radii decreases. Generally, as you go, it'll decrease, and then sharply increase, then decrease as you go across to a new block. Yeah, that's really it. So, thanks for watching. Don't forget to like, subscribe, all that stupid stuff. Until next time.